Oh, dang it.
Okay, thanks. Am I full screen now?
Yes.
Okay, great. Yeah, so thanks for the invitation to give this seminar today. My name is Mika, and I work for the Norwegian Meteorological Institute, or I'll probably use the shorter name Met Norway in this talk. So we're a governmental organization similar to NOAA in the US. So we're responsible for issuing national weather forecasts, but we also do a lot of research on pretty like basic atmospheric, ocean, and climate sciences. So our headquarters is in the capital Oslo, but I'm actually based at a sign branch in Bergen, which is a town on the west coast of Norway. And in recent years, I've been focused on working with wave observations in the oceans around Norway and also some other regions as well. So in this talk, I thought I'd focus on wave measurements, especially in deep waters, so far from the coast. And I'm going to describe how we're developing and implementing innovative new methods for measuring waves, both at my institute, but also more generally within the broader research community. So this slide is just a quick outline of my talk. I'll start with a brief intro to wave theory, and after that I'll describe the types of wave-related research that we do at Met Norway. Then I'll give a brief description of some traditional methods and instruments used to measure waves in the ocean. And I'll follow that with a description of some more novel techniques that we're working on these days at Met Norway. At the end, I'll also present some preliminary results from a pretty exciting recent field campaign where we tried to measure waves both from above and below. So I'll talk more about that a bit later. So this is just a basic intro slide to wave theory, specifically random waves and the wave spectrum. So when we talk about real waves in the ocean, we usually talk about the general sea states, which is a function of the fetch, or the distance over the wind, which the wind blows on the sea surface, the strength of the wind, and the duration of the wind forcing. So basically, the stronger the wind, the longer it blows, and the larger of an area that it blows over, the larger the waves get, and the rougher the sea states. So it's a pretty convenient and very common simplification to think of the full messy wave field of a sea state as a superposition of a large number of elemental harmonic wave components. So we can write that in this way, where the sea surface eta here is composed of a large sum of harmonic waves with random phases and random amplitudes. So this randomness also means that we usually think of waves as a stochastic process and not a deterministic one. So from this kind of Fourier representation, it also follows quite naturally that we can represent the sea state in spectral form. So this is a one-dimensional wave spectrum where the frequencies of all those individual wave components are on the x-axis, and the y-axis shows the wave energy density or the variance of each of those components. And the spectrum can actually give us a lot of information about the sea states. For example, the frequency of the peak energy gives us the period of the most energetic waves. So in this case, the peak frequency is around 0.1 hertz. So that means that the wave period is around 10 seconds, which is a pretty common wave period in the ocean. So we can also integrate the spectrum over all frequencies and we get the full variance of the sea surface, which we write here as m naught. And we can use the sea surface variance to give us an estimate of the so-called significant wave height, which you can think of as the wave height that an experienced visual observer would give for a given sea state. And there's also an official definition which says that significant wave height is the mean of the highest 1/3 of the waves observed during a given period of time. And the spectral estimate is usually pretty close to this value. So we can also numerically simulate the wave field. if we, for example, want a wave forecast for a certain location. So most commonly, especially for large domains, for example, the Norwegian seas, like in the figure here at the bottom, we actually simulate the evolution of the wave spectrum and not the individual waves themselves. So in these models, we usually also include the wave direction in the spectrum so that we can tell where the waves are headed to and coming from. And the spatial and temporal evolution of the spectrum is represented in terms of what they call source terms. These are shown in the equations here. These source terms are basically parameterizations for the effects of nonlinear processes that we don't have simple analytic formulas for. So the most important source terms in deep water far from the coast are the input of energy by the wind and the removal of energy or dissipation of wave energy by breaking, which is also called white capping in the open ocean. And then there's also a third source term for nonlinear interactions that shuffle energy between high and low frequencies. And at this moment, there's still quite a lot of research going on to fine tune these source terms, and especially the wave breaking source term has quite a lot of uncertainty associated with it. So next, I'll give a somewhat incomplete overview of wave-related research at our institute. So as I mentioned earlier, we do a lot of weather forecasts for nearby regions. And in our case, we also do a lot of wave forecasts using the spectral wave models that I just described. So we run a pretty large number of different wave models for different domains and also at different resolutions. And anyone who's interested can download the forecast output for free from our servers that I'm showing here. We also study the wave climate, so running our forecast models for historical periods using historical observations and reanalyses. And these so-called hindcasts are really important for a lot of commercial offshore activity, where new constructions need to consider the most severe sea states that can be expected for the location that they might want to, for example, build an offshore wind park in. So if we step away for a moment from the spectral representation of the waves, another big area of research for us is in individual wave statistics, where we're interested in knowing just how big of a single wave we can expect in a given sea state. So we usually test the statistical models on wave time series, like the one at the top here, which we get from wave buoys and other devices installed on, for example, oil platforms. And the plot on the bottom is a crest height exceedance probability plot, where the x-axis is the individual wave crest elevation normalized by the significant wave heights, and the y-axis is the probability of encountering such a crest for a given sea state. So these kinds of statistics are important for the shipping industry. This figure shows cases where marine accidents are believed to have happened due to so-called drogue waves, or waves that are much higher than one might expect to encounter for a given sea state. There have also been accidents where large waves hit actual oil platforms with fatal consequences. So the platform operators also need to be able to trust the statistical models to know when to evacuate the platforms, for example. Waves are also important in the climate system, and especially the whitecaps or deep water breaking waves, which influence air-sea gas momentum and heat exchange. They also drive upper ocean mixing and release sea spray aerosols into the atmosphere. And whitecaps can also actually increase the reflectivity of the ocean surface, which can have an impact on how much solar radiation gets absorbed by the ocean. And this plot on the right from Reichel and Dijke, 2020, also shows the importance of bubbles created in the breaking process. And we see a pretty clear correlation between regions of high bubble concentrations on the left. So these are basically regions with very high wind speeds and a lot of white capping, and the net air CO2 flux on the right. So now I thought I'd briefly describe a few traditional wave measurement devices and what they're typically used for. So a common instrument on fixed platforms, such as oil platforms, is a laser altimeter or some other kind of probe or a wave staff. And these can typically operate at high temporal resolution, so they can resolve both individual waves and also wave spectra. But they can usually only measure a very small point on the sea surface and don't really give any information about the wave directionality. Wave buoys are another very common instrument. These can typically measure both individual waves and spectra also. And some more modern buoys can also give you directional wave spectra. So these are really useful for validating spectral wave model output. Marine radars can be used to estimate directional wave spectra, but the quality of the measurement, especially for the wave heights, tends to be pretty sensitive to having a really good calibration. And finally, satellite altimeters are also used to get estimates of wind speed and significant wave heights. And these observations cover pretty much the whole globe, but they're usually pretty coarse resolution, and it usually takes a few days to get a new measurement for the same location again. So some limitations of these kinds of traditional instruments, these are typically commercial hardware and software. And for this reason, they're difficult or sometimes even impossible to customize for your own needs. They're usually very expensive to purchase and operate, and also to maintain. They usually have either a limited temporal resolution or limited spatial coverage. And usually, because these instruments are very expensive, you don't want to get several of them for the same location. So it can be difficult to validate the measurements that you get from them. So how are we currently trying to improve on these traditional wave measuring methods at Met Norway? So one area that's in pretty rapid development in recent years are these kind of small scale and low cost drifters that usually come with GPS for tracking their trajectories and accelerometers or inertial measurement units or IMUs for getting the wave heights. These open source buoys are usually quite simple to assemble with pretty easily available components. There's currently several institutions developing their own kind of models, and usually they use open source processing and also data transmission software. Currently, they're largely used for research experiments, but there's also commercial potential in these devices. So currently at Met Norway, there are two pretty closely related open source wave drifter projects under development. I should give full disclosure here that I'm not personally involved in developing these instruments, but the original wave drifter is called the Open Met Buoy, or the OMB, and it uses the Iridium satellite system for transmission, so it can basically be deployed anywhere in the world. A slightly more recent development is shown on the left. This is the SFY buoy, and this one transmits data on the cellular network, and it records data at really high temporal resolution. I think it's something like 50 hertz. So both of these designs are fully open source, and the source codes are also available on GitHub. So these kinds of wave drifter buoys are very cheap to build. You can build them from scratch by buying the components yourself, or in the case of the OMB buoy, you can even purchase them fully assembled for around $1,000 US, which is quite a lot cheaper than buying a commercial wave buoy. Because these are very cheap and fairly easy to build, you can also deploy them in very large quantities. So this figure here shows a recent experiment where they deployed a lot of these OMB drifters in the Arctic for a pretty long experiment. And because they're cheap, they can also be considered quite expendable. So you can use them in very rough conditions and locations, such as this experiment here, where they use the SFY buoy to measure accelerations in plunging breaking waves in the surf zone. So stereo video imagery is another relatively new development for wave measurements. And this is basically a machine vision technique that uses pixel matching and triangulation to reconstruct a 3D scene of the sea surface from a pair of synchronous photos or video frames. So this technique is also relatively low cost. All you need is basically a pair of synchronized cameras. You need some lenses, and also you need some hardware for doing the actual acquisition and processing. There's also some very useful open source software available for this kind of image processing. We've had really good results from using the Waves Acquisition Stereo System, or the WAS software, which is developed by some researchers in Italy. So this stereo video technique provides high resolution wave field reconstructions where you get both spatial and temporal coverage at fairly high resolution. And in addition, for validation purposes, it's very useful to actually have the actual raw imagery. Of course, one limitation with this method is that you can't really see what's going on under the surface. So this is a bit problematic for studying processes related to wave breaking, for example. Yeah, so now I'll go on to showing some results from our datasets. And this here is basically our open air wave observatory. It's called Ekofisk, and it's technically an oil platform that's located in the central North Sea, as you can see in the little map there. The platform is operated by ConocoPhillips, and we've had a really good relationship with them for decades now regarding testing new wave measurement devices on their platform. So on this walk bridge connecting the two platforms, they have an array of 4 laser altimeters that record the distance to the sea surface continuously at 5 hertz. This system has been in place for over 20 years now, and it's given us a lot of really valuable data. And also, because we have 4 identical lasers so close to each other, we're relatively easily able to verify measurements of really big waves so that we can be sure that we base for example, our statistical models on real extreme waves and not on measurement errors. We've also had a stereo video system on the platform for quite a few years now. This system was installed in 2017. It's been producing raw data for more or less continuously since then. Of course, we're not able to process all of the images that get taken, but we do have, at this point, what I believe is the most comprehensive offshore stereo video dataset pretty much anywhere in the world. And just to quickly summarize how we do the wave field reconstruction from the stereo video on the platform. So we start with the sequences of synchronized frames from the two cameras. Then we do some image processing that includes pixel matching and triangulation. This gives us a three-dimensional point cloud where each matched pixel gets a 3D world coordinate. And when we do this sequentially for each image pair, we get a four-dimensional time series of the sea surface, as you can see in the animation on the right here, where I projected the point clouds over the original raw camera frames. And for analysis, we usually rectify the point clouds and interpolate them onto a regular 2D grid, which gives us this three-dimensional time series of the sea surface elevation that you can see on the bottom right. And I'll just give a mention again to the open source WAS stereo processing software that we're using, and that's given us really good results so far. Yeah, so now I'll get to a recent experiment that we've conducted on the platform. So about 2 years ago, we got permission from ConocoPhillips, who operate the platform, to do a field experiment at the Ekofisk field, where we temporarily installed an upward-looking acoustic Doppler current profiler, or an ADCP, within the field of view of the stereo cameras. So I should say again here that I'm not the main person in charge of this project, and most of the results that I'm showing here are from my colleagues Trygve Halsne and Maria Bjørnestad, who also work as researchers at Met Norway. I should also say here that the ADCP is definitely not a cheap open source device, but it's an instrument that's starting to be implemented more and more recently for studying bubble clouds from breaking waves near the sea surface. And if you remember earlier, I mentioned that bubbles from whitecaps are the main driver of air-sea gas fluxes. But until now, I don't know that anyone has actually managed to measure the wave breaking process both from above and below the sea surface at the same time. So that's what we're trying to do here. So the ADCP that we used in this experiment is a Signature 500 built by Nortec. And it has 5 sonar beams, out of which 4 are slanted at an angle, and 1 points straight up in the vertical. So it turns out that bubble plumes are very clearly visible in the backscatter intensity of the ADCP beams. And you can see an example on the bottom right, where we've set a threshold on the backscatter intensity to identify the depth that the bubble plumes reach below the surface. That's kind of shown in gray here in the image on the lower right. And next to that, we see kind of the geometry of the ADCP beams projected onto the sea surface elevation reconstructed from the stereo video cameras. So in these figures, you can see the approximate position of the vertical ADCP beam footprint on the raw imagery from the stereo video cameras. In the middle, I'm showing the camera view, and on the right, the rectified view, kind of looking straight from above. We're also using pixel thresholding to identify the whitecaps in the raw stereo camera frames. And we use these whitecap estimates to try and compare the whitecapping that we see on the surface to the bubble plumes that we see below the surface using the ADCP. So the ADCP also gave us a really good opportunity to validate our stereo video reconstructions. Here on the right, we've plotted the sea surface elevation time series from the stereo video at the point where we assume the vertical ADCP beam hits the surface. So kind of around the black dots on the grid, the stereo video grid on the left. And on top of the time series from the stereo video, we've plotted the actual surface measurement that we get from the vertical ADCP beam. And we see that the two waveforms or the two wave signals are basically identical, and their correlation is around 99%. So this was really encouraging to see, really validated our stereo video measurements. And also the stereo video, of course, validated the ADCP measurements. So let's see if this video will work. Yep. So this is the last results slide that I'll show today, I think. And this is an animation where on top we see a sequence of stereo video frames from a day with quite a lot of whitecapping activity. The red dots are the synchronized positions of the 5 ADCP beams that we've projected onto the sea surface based on their accelerometer measurements. So we see that the ADCP rotates pretty strongly on its mooring line. So the slanted beams move around quite a lot. Let me play this again. But the vertical beam actually in the middle actually stays pretty stationary. Then in the middle panel, we show the stereo reconstructed sea surface, and the bouncing dots below are estimates of the bubble plume depths from each of the five beams. And on the bottom, we show the corresponding bubble plume depth time series, where the messy colored lines are the estimates from the slanted beams, and the black line is the bubble plume depth estimate from the middle vertical beam. So we can see that it's pretty hard to detect, we see that it's pretty hard to detect a clear correlation between the instantaneous bubble plumes and the surface whitecaps. And we think that this suggests that there might be other more indirect circulations going on that affect the advection of plumes more than just the direct ejection of turbulence by the breaking waves. Yeah, so to summarize the preliminary findings of these experiments, we find that bubble plumes are very non-local and also spatially heterogeneous. We can't find a direct connection between the bubble plumes, especially the deep bubble plumes, and the whitecaps on the sea surface. And we hypothesized that the plumes might be advected both horizontally and also vertically by other mechanisms, such as potentially Langmuir circulations, which are a process that happens due to wave current interactions. Yeah, I might be a bit ahead of schedule here, but this is my last slide. Just to summarize what I've been talking about today. So these advancements in technology that we've seen in recent years have enabled us to develop novel wave measurement systems that are both cheaper, easier to use, smaller in size, and more flexible than many traditional wave measurement instrumentation. You could say that these new developments kind of democratize the wave research landscape by enabling innovative experiments with significantly reduced costs. And we can also use these novel methods together with established instruments, such as in the ADCP experiment that I just described. And we can integrate these techniques to provide new insights into complex phenomena such as bubble plumes and breaking waves in the ocean. So yeah, thanks. I can take any questions at this point.
So, any questions from our friends online? Abigail, Domenico?
Yes, I have a question. Oh, sorry.
No, Abigail, Domenico, can you go? We start with Abigail and then we do Domenico.
Awesome.
Abigail?
So I was wondering, do you know if anyone else, like at the department that you work in, is using this kind of wave mapping data for like any wave energy, renewable energy programs?
Do you mean this kind of stereo video data?
Yes.
I don't think they're doing it directly at the moment, but there definitely is a lot of potential for that. They've also been using these low-cost drifter buoys that I presented earlier for a lot of experiments where they can kind of deploy a lot of those buoys to get kind of extended spatial coverage as well, which is useful for these kinds of applications, I think.
Awesome. Thank you.
Domenico?
Yeah, I was wondering if there is any device or technique that can give you information about what happens right below the water level.
Yeah, so one of the limitations with our ADCP experiments is that we had to install the ADCP pretty deep down. It was at around 40 meters depth, if I remember correctly. So that means that due to the way that the instrument works, we can't really resolve what's happening very close to the surface, which is also where the most energetic turbulence is going on, for example. So there have been other institutes that use ADCPs mounted on larger wave buoys, where they install the ADCPs to look downward from the bottom. So this is one way that we can actually get pretty high resolution both turbulence and current and bubble measurements very close to the surface. But as far as I know, people haven't been able to use these kinds of buoy measurements together with, for example, stereo video cameras. So you're still lacking a picture of what's happening from above the surface.
Okay, thanks.
Thank you. What about here in class, in the classroom? Any questions? Okay, thank you very much, Mika.
Thank you.
So, and maybe I'll see you at WISE.
Hope so.
Okay, thank you.
Thanks.
Okay, I'll see you. I'll send you the summary, okay? Let's see what AI. Let me stop it now.
Which AI is